Welcome back to Particle Physics in 10 Micro Lessons. I'm Richard Feynman, and today we tackle one of the deepest mysteries in science. Why do things have mass? Why do some particles weigh a lot, while others, like the photon, weigh absolutely nothing at all? For decades, the Standard Model had a glaring hole. It predicted that all fundamental particles should be massless, zipping around at the speed of light. But we know that's not true. We have weight, atoms have mass, and the universe isn't just a spray of light. In 1964, Peter Higgs and others proposed a radical solution, an invisible field that permeates every single cubic centimeter of the universe. We call it the Higgs Field. Imagine it like a cosmic molasses, or a thick syrup that fills all of space. A photon, a particle of light, doesn't interact with this field at all. It zips through the syrup like it isn't even there. But other particles like the electron or the heavy W boson get bogged down. They interact with the field, and that interaction is what we call mass. The more a particle interacts with the Higgs field, the more mass it has. It's a dynamic, constant exchange. Think of a celebrity walking through a crowded party. The more famous they are, the more people cluster around them, slowing them down. That cluster is mass. But what about the God particle everyone talks about? The Higgs boson isn't the field itself, it's an excitation of that field. If you slap a giant vat of molasses, you create a ripple. That ripple, that concentrated bit of energy, is the Higgs boson. To find it, we had to slap the field harder than ever before. We built the Large Hadron Collider, a 17-mile ring beneath Switzerland. We smashed protons together at 99.9999% the speed of light, recreating the conditions of the early universe. In 2012, physicists at CERN finally saw it. A tiny bump in the data, a signature of a particle weighing about 125 billion electron volts. That's about 133 times more massive than a proton. The discovery confirmed that our theory was right. The field was real. So, why should you care? Without the Higgs field, electrons would never have slowed down enough to orbit an atom. No atoms means no chemistry. No chemistry means no DNA, no stars, and certainly no physicists. The Higgs field is the invisible glue that allowed the universe to cool down and form the structures we see today. It's the final piece of the main Standard Model, but as we'll see in our final lesson, it opens the door to even deeper mysteries. Some physicists think there might be more than one Higgs boson, or that the Higgs field itself might be unstable. But for now, we celebrate it as the cornerstone of mass, the reason you can sit in your chair and I can hold this piece of chalk. We've covered the forces, the quarks, and the bosons. We're nearing the end of our journey through the subatomic world. Up next, we look at the universe's reflection, antimatter. Why is there something rather than nothing? Until next time, keep asking why. I'm Richard Feynman for James's Physics 101. Thanks for watching. Make sure to check out the full Particle Physics in 10 Micro Lessons playlist to master every piece of the puzzle. Subscribe to James's Physics 101 for more deep dives into the fundamental laws of our universe. See you in the next lesson.